Good morning, I'm Professor Mohamed-Nabil and I'm going to develop new ideas about rational modeling of forced convection heat transfer. This is a paradigm shift that I am proposing. Ideas will be totally out of the box. Some readers have found this already good ideas, interesting, etc., creative. Some others have found them completely silly. This is normal when you make a paradigm shift. We have to expect and accept this and even respect this. But it is still, in both cases, still an interesting exercise for you to put in question ideas that for you are well established, and then after examining the implications, you may come back to the new ideas and say, to the old ideas, and say that new ideas are silly, or consider changing your ideas. So be a little bit patient of me and go with me through my argumentation, and let's see what will happen. Let's go. What is the objective of modeling? The main objective. Suppose I have an object omega that is exchanging heat with its surroundings through the surface d omega, or maybe inside the heat transfer developed inside the model, and I want to be able to predict temperatures and heat fluxes everywhere. Now, for that we need the following. We need first the governing equation, which is the heat transfer equation or the energy equation that we all know. And also I need boundary conditions on d omega, which might be either Dirichlet type, I give you the temperature, or Neumann type, we give you the heat flux, or Robin or third order type, where I give you a relation between temperature and heat flux. Now, if I have this, I can get temperature and heat flux everywhere, mainly on the boundary. That is something that is of most interest for engineers. Now, we don't always use the partial differential equation because it's a complicated thing. We cannot always obtain an analytic solution, and even if we do a numerical solution, it's not that simple. It's a rather complicated issue. So we usually revert to another replacement of the partial differential equations, which are called the detailed model. We replace it, but we call a compact thermal model, CTM. This is a simple set of equations, sometimes only one equation, that should replace the partial differential equation, not the boundary conditions, the partial differential equation. I can use these simple equations together with the boundary conditions imposed in order to predict temperatures and heat fluxes. But there is one important notion that I have to respect, is that these CTMs should be boundary condition independent, which means that the model should work well with any kind of boundary conditions, not only one kind, any kind of ones. Otherwise, it's completely useless. This notion of boundary condition independence, BCI, has been developed by a dear friend of mine, in fact, Clemens Lazarus, to which I am saying hello. He has done a lot of contribution to the heat transfer community by introducing this notion and many other notions, by the way. Now, one of the compact thermal models approaches is to replace the whole object by a single resistor. It is called the single resistor compact thermal model. But this cannot be always done. There are some restrictions, so we have to make some assumptions in order to be able to do that. Now, let us assume that we have only heat transfer by the surroundings, not inside the domain, and that this is done through only two regions. We call that each region is called a thermal port. It's a region where heat is transferred to or from the object. Other regions are considered as insulated. Okay. Now we will make these two simplifying assumptions. First, that we have only two ports, we can develop the same notions with 3 or 4 ports, but let us present the things in a simple or the simplest possible way. We have only 2 ports, A and B, and the temperature is uniform over each port, A or B. Of course, different between the 2 ports, but uniform on each port. Now we can develop the argumentation I'm going to show also for the case where we have, instead of uniform temperature, a uniform heat flux. But the results are the same. So I will keep the only one temperature is uniform over port A or port B, and port B. Now, if I do these assumptions, then we can replace the object by a single resistor connecting the node, not the port now, the node TA, which is the single temperature prevailing over port A, and the node TB, which is a potential, the single temperature prevailing at port B, and between them we have a resistor, and heat is flowing out of TA into the object called QA, and out of TB into the object is called QB. Of course, they are the same with different signs. That is, QA plus QB is equal to 0. When I do this, I can present the model in the form of delta T is equal to a certain resistance multiplied by Q, just like the Ohm law. Okay. Now, some algebraic manipulations in order to put this in the matricial form, which will be useful for the sequel. First, I will define a temperature, reference temperature, which is the average TA plus TB over 2, and then I will define TA star, which is TA minus TRF. TB star is equal to TB minus TRF. When I do that, then the single resistor equation can be cast in the matricial form, either a vector on the left, TA star, TB star, and another vector on the right, QA, QB, related by the 2 by 2 matrix, which is the resistance matrix, or I can put it in the inverse form, of course, QA and QB a vector on the left, TA, TB a vector on the right, and between them you have a matrix of admittances, 2 by 2 matrix. They are both equivalent, of course. It's just a useful presentation way. Now, what happens if the temperature was not uniform on each port? I will start with only one port. TA is the only temperature that is not uniform. Along the coordinate x, which is along the port, the temperature TA may be function of x. I will assume that temperature at B is still uniform. Now, I will also take the simplest ever dependence of temperature on x, which is a linear dependence. TA is T average times 1 plus A, which is something like the temperature gradient, x over L over 2. Now, if A is 0, then we come back to the uniform temperature. But A may be positive or negative, temperature increasing, decreasing, whatever, can be strong, not strong, etc. But we will limit our presentation for the moment for linear variation. In this case, we have different heat paths. Heat paths from the left side of TA until TB may be different, or may have a different thermal resistance from the heat path on the right of TA until TB. It's called R right. It may be different because paths may be of different lengths, or it may encounter materials of different thermal conductivity, etc. In general, we may have two different thermal resistances, R left, RL, and R right, RR. And the equivalent or overall resistance, I will revert now to the admittance, is the sum of these admittances which are in parallel. 1 over RTH, which is the equivalent, will be the sum of these two resistance, but we have to take care of these two impedances, in fact, but we have to take care that the temperature difference over each path is not the same. So at the end, we will obtain an equivalent thermal resistance or equivalent thermal impedance, admittance, which is function of A. That is, it's a model that depends on the boundary condition, which means it's a completely useless model. But I would have to do that if the temperature was varying with X. Now, another approach is to subdivide the thermal port A into A1 and A2, assuming that on each subdivision we have almost a uniform temperature. The same between B can be divided into B1 and B2, and hence we will have first a resistance between A1 and B1 called R left, and between A2 and B2 called R1 or R1 and R2, as well as a resistance between A1 and B2, A2 and B1, and maybe, why not, between A1 and A2 if they are at different temperatures, then heat may flow from one to the other, and B1 and B2. So at the end, my model will be is a bigger matrix composed of 4 temperatures on 4 ports on the left, a vector, and another vector of 4 heat fluxes out of the 4 ports, and in between them there is a matrix now, a little bit more complicated matrix than if the temperatures were uniform and if we had only 2 ports. Now we have 4 ports. There is a myth I want to dissipate between the heat transfer community, which is about the complete analogy of electricity and heat transfer, electrothermal energy. This is a myth, it's not true. And in order to prove it, I will start with my Turkish coffee pot. It is made of stainless steel. It has a stainless steel handle, same material, that is a little bit long to make something like a fin. And then in order to prepare my Turkish coffee, in order to do it, I have to add some coffee to water and put the whole on a very light fire. It should be on the incipience of boiling, and I keep it on this incipience for a couple of minutes until it is cooked. And then, okay, but remember, I am taking this handle by my hand. This is a real picture, and I don't feel anything hot. Maybe a little bit warm, but not hot. I can handle it, no problem. The temperature at the base of the pot, let's say a little bit greater than 100 degrees centigrade, maybe 110, something like that. Now, what would be the equivalent of the electricity? Remember, stainless steel is a very good thermal conductor. Air around is a very bad thermal conductor. They are the same good, stainless steel is a good electrical conductor. Air is an electrical insulator. Assuming that I have put 110 volts on the base of the teapot, the same teapot, same geometry, same materials, etc., will I be able to handle it with my hand? No. The voltage at the end of the tip will still be 110 volts, but the temperature at the end of the handle will be something like 30 degrees centigrade, something like that. I didn't really measure it. And why is it so different? Because of electrical conductivities, steel over air is something like 10 to the power 18. But the thermal conductivities of steel divided by that of still air is only 400. And the ratio may be even smaller if the air was allowed to move. Even if I assume still air, the ratios of conductivities is far less great than that of electrical conductivities, which means that an electrical conductor is a very, very good conductor. You will have the same potential everywhere. But the thermal conductor is not as good. You will not have the same temperature everywhere. The same for air. Air is a very good electrical insulator. No single electron will escape through air. But from the point of view of thermal, air is an insulator, yes, but some heat will go through air. And that's why we cannot say that there is an analogy. In fact, for electrical domain, having an equipotential over a node, an electric port, in fact, is something normal. That's on every electrical port, you will have a uniform electric potential. But from the thermal point of view, it is never the same. You will never have a uniform temperature in real life because of these differences, large differences in electrical conductivities and thermal conductivities. Now let us look at the convection problem. Suppose I'm having a fluid flowing inside a duct, solid, and then I'm heating from the outside of the duct by uniform heat flux, and there is a flat temperature profile at inlet. Okay. Now, of course, since I'm heating, at the outlet the fluid is hotter than at the inlet, which translates into a temperature gradient inside the solid also. The solid temperature at the outlet or near the outlet is higher than the solid temperature at the inlet, which will cause a heat flux through the walls. And this heat flux will influence on the net flux arriving to the fluid. Even if the flux outside the solid wall was completely uniform, the flux arriving at the fluid, or the flux at the fluid, or at the flux at the interface between solid and fluid will not be uniform. In fact, having a uniform heat flux is very difficult. Having uniform temperature is also very difficult, as I have explained before. But this is not the whole story. At the inlet, suppose I am saying flat temperature profile at inlet. This is not really possible in reality, because assuming that means that the temperature gradient normal to the fluid flow is zero, which means there is no heat flux in this direction. Well, but at the inlet near the wall, you have the maximum heat flux, in fact, not zero. So there is a contradiction here, a singularity. Temperature profile at inlet cannot be uniform in real life. The same will happen if I don't add heat flux from the outside, but I have two tubes, or a tube and an exterior fluid flowing inside the duct and outside the duct in a co-current or counter current, etc. You will always, in this case, never have a uniform heat flux. So neither heat flux nor temperature may never in reality be uniform. Okay, let's go to the heart of the problem, trying to model forced convection. I have the energy equation, which is in yellow, the upper left side, together with a certain number of boundary conditions. We may specify the temperature or part of the boundary, heat flux on another part, or even a third type boundary conditions, which is also called Robin, in which I am giving you the relation between heat and delta T, and neither heat nor delta T. Okay, this is an elliptic problem. We have Laplacian T somewhere, which is there is a very well-known fact that you cannot predict temperature anywhere inside the domain if you do not specify a boundary condition anyway all along the boundaries. If there is only one part that is missing, then you cannot solve this problem. Let us try to explain this with a simple 2D problem. It can be a conduction or a convection problem. They are both elliptic at this level. So let us take a 2D plate that is insulated on the left and right sides of the boundaries. That is, I'm giving you Q equals to 0, and then let us assume that I'm giving you the temperature on the bottom wall, say 100 degrees, for instance. And I'm not giving you any boundary condition at the top wall. Okay, and if I ask you now a question, what is the temperature inside the domain close to the bottom wall where temperature is given? You should normally say, I don't know, because there is a missing boundary condition. In fact, if the temperature at the top wall was, for instance, 0 degrees centigrade, then the temperature will decrease gradually from 100 to 0, and the point I'm asking for might be at 98 degrees or something like that. But if the temperature on the top wall that I don't know was 200, for instance, then the temperature will increase gradually from 100 to 200, and the temperature at the point I'm asking for would be maybe 102 degrees centigrade, something like that. So because this heat is a diffusion problem, physically speaking, and because it's an elliptic problem, mathematically speaking, we cannot predict the temperature anywhere inside the domain if we do not have boundary conditions everywhere at the boundaries of this domain. Let us reconsider this fact for a convection problem. We have fluid flowing in a duct and heated by the walls. The dotted line represents the evolution of the thermal boundary layer. Now, because the problem is linear, if it's a forced convection, then the velocity is known, and then the energy equation will be an equation in the temperature only, which will be linear, as you can see. And because people would usually make the assumption of local relation between delta T at any section and Q at that same section, then people would expect that the result would be linear in the form Q is proportional to delta T somewhere. Okay, this is not a good assumption. And in order to prove that this assumption is silly, Robert Moffat, a good friend of mine and has made many good contributions to the science, in fact, has imagined the following experiment. Suppose I insert a small insulating element, small in size but strong insulation. Then temperature at the wall will not change a lot. It will increase a little bit, but because of diffusion through the walls, it will still remain at the same temperature it was before inserting this insulation. The same goes for the fluid. Due to both diffusion and convection, the temperature beneath this insulation will not really change a lot. So delta T will be basically the same. However, Q may eventually go to 0 at that point. So you have a delta T without adding heat. Should I say H is 0 at that point? Maybe. But in this case, we will normally ask the question, why do I have delta T if I don't have heat? That's why Robert Moffat has invented a concept he named the adiabatic heat transfer coefficient. I'm not using this concept, but at least it explains to us that the local assumption is not a good assumption. I'm giving now another example that I have read it somewhere, but I don't remember where exactly. So unfortunately, I cannot tell you who is the author. But now I have boundary conditions in terms of temperature. Assuming I have a temperature T1 at inlet, that is rather high, and then suddenly goes down to T2 after a certain distance. Both T1 and T2 are still higher than those of the fluid. So the fluid is being heated, by the way. Now, beneath the first part, T1, I have a solid thick line representing the temperatures inside the fluid. And when I enter into the zone beneath T2, just after the transition, I have a solid thin line beneath that point. Notice that there is a thin layer close to the walls that has normally rather high temperatures, related to T1 in some sense, that can be higher than T2, but the bulk fluid may still be at a temperature smaller than both T1 and T2. And then we will have the following peculiar situation in which, although the wall temperature is higher than the bulk temperature, heat will flow, in fact, from the fluid to the walls, because it will flow from the thin hot layer just next to the walls to the walls. In this case, if I'm still blindly assuming that the relation between delta T and Q is local, then I will have to define a negative heat transfer coefficient, for instance. It's completely silly. It contradicts the second law, and the problem is not in the second law. The problem is in this wrong way of modeling, saying that delta T at a given section depends on Q in only that section. It must depend on it, but not only it. It should depend on all what happened upstream and downstream. So heat transfer is not a local problem. Local H is in contradiction with both physics and mathematics. The relation Q is proportional to delta T, which is a linear relation, is not a good one. We must find another relation that must still be linear, because the problem is linear. How can you find something that is non-linear? But Q proportional to delta T is not the only linear relation. And what I'm going to propose is another linear relation. Some notes about the analogy between vectors and functions. What is a vector? If I have Vi, for instance, where I runs through the set of natural numbers 1, 2, 3, etc. For each natural number, I have a mapping. A vector is a mapping of n into R. V1 corresponds to 1, V2 corresponds to 2, etc. The function is also, if I have a function of x, x being a real number, it's a mapping of R into R. We have x, we have a certain number of points, an infinite number of points, by the way, x1, x2, x3, etc. And for each value of this, I have a corresponding value of f, f1, f2, f3, etc. So this represents a certain analogy between vectors and functions. The analogy goes a little bit farther than that. I will show that now. Normally, when we represent functions in any numerical problem, we have to make a meshing. And instead of obtaining the function f over all infinite number of points, I will have to obtain it over mesh points only, which is a finite set that can be numbered from 1 to n. In this case, the function becomes a vector. This is called the nodal representation of a function. Nodal comes from node, because I'm obtaining f at different nodes. The analogy goes a little bit further. Usually, we can represent a vector by developing it over a basis of known unit vectors. For example, in Cartesian coordinates, I would say that v is vx I being the unit vector in the x direction, vy j, etc. It can be done for cylindrical coordinates, for spherical, whatever you name it. Now, we do the same normally with functions, by the way. We develop the function, for example, in Taylor or Fourier or Chebyshev or whatever series you want. Let us use Taylor. A naught x to the power 0 plus a1 x to the power 1, etc. Now, I can collect the set of coefficients a naught, a1, a2 in order to make of them a vector. This is called the modal representation as opposed to the nodal representation of. Modal comes from the mode, because if I use Fourier series, normally we have sine x, cosine 3x, etc. Everyone is a mode of vibration, and this is the name comes from that. Usually, we never deal with an infinite series. We always have to truncate it. And when we truncate it, we have a finite set of coefficients, a naught, a1, etc. And hence, the function becomes a vector, simply. Now, my question now is the following. I want to obtain the general linear relation between two vectors, that is two functions, that is two vectors. Q, that is a space function, and delta t, that is another space function. What should I put in between? The yellow thing here, mysterious thing. Is it a scalar, like Q is equal to H delta t? Well, this is a very special case. It's not the general case. In this special case, delta t and Q are vectors having the same direction. In the functional space, these are two functions that are similar but multiplied by a constant. This is a very special case. The general relation between two vectors is a matrix. And when I go to the functional space, the general relation between two functions is an operator that operates on a function to give me another function, instead of a scalar going from one function to another function. So the general linear form between the function delta t and the function q is this integral linear operator, in which delta t at a given section depends on q on all the boundaries, both at the point where I am applying, I'm studying delta t. Of course, we have to have a weight like g, because at the point I'm studying delta t, q at that point as well as q at neighboring points will have a large influence on delta t. Q at points that are far away will have a small influence. This g, by the way, is the green function, as I will show in the next slide. But the most important thing, that this is a linear relation, but it's a general linear relation, as opposed to q is equal to delta t, or delta t is equal to q over h. And we will see how can this general form be reduced to the special form. We will find that this is done only in very strong assumptions. So let's say a little bit about the form of the new approach. Suppose I will start by the partial differential equation as you have, and then beneath it we have a set of boundary conditions that are put inside a blue rectangle. And I want to obtain an equivalent compact model equivalent to the partial differential equation, but not be contaminated by any boundary condition I may impose, because I want my compact model to be totally boundary condition independent. To do this, I have suggested what I have called a generalized green function. It looks like the green function with a small difference. The green function, in fact, satisfies the joint partial differential equations as that of the temperature. I say joint because even number derivatives will be the same, but odd number derivatives should have different signs. So the green function is a solution of the same equation, of the joint equation, in fact, with a heat source that is a Dirac, I mean a point heat source. Okay. Boundary conditions, normal green functions is homogeneous, but in the generalized green function I cannot make this. Why? Because if I say, for example, it's heat equals to 0 all over the boundary, it will not work, because I have a heat source which is a Dirac localized somewhere inside the domain, and this Dirac will dissipate heat inside the domain, which should go out from the domain. It cannot accumulate it, otherwise it will be an unsteady problem. So it will go out from maybe a tiny small region in the boundaries. So all the boundaries will be insulated, that is homogeneous boundary condition, like the normal green function, except a small part in which heat is allowed to escape, heat that has been produced by the Dirac. Okay, now I will use the original partial differential equation as well as the generalized green function and make some algebra that are outside the scope of this presentation to obtain this form, where G is the green function. Delta T, which is T minus Tref is the reference temperature, which is, by the way, can prove that equals the average temperature on the small portion where the heat escapes. The average temperature on this becomes now a reference temperature. T minus T reference is equal to two integrals using the same green function, by the way, one of them relating heats inside the domain QV and the other heat outside the domain QS. I will not consider the first one in the sequel just for simplicity, which gives me the delta T is equal to an integral of G times Qs, the surface heat flux, which means that the surface heat flux everywhere in the domain should have an influence on delta T anywhere in the domain. This is the correct way of modeling things that respects the analytic, the elliptic behavior of the partial differential equation, and also respects physics, as we have seen in many examples. Notice that boundary conditions were never used during this algebra at all, which means that the equation I obtained in white is boundary condition independent, BCI. Now, this relation should replace the partial differential equation, and it does. And this is a general boundary condition independent linear model. I have to use it together with boundary conditions in order to obtain TS and QS, temperatures and heat fluxes on the surface. Now, how about the heat transfer coefficient, HTC? Suppose I still have a flow over inside the duct, and Q outside, entering this fluid is a function of X, and delta T is also a function of X. So I have this relation. Now, can this relation boils down to delta T is equal to 1 over H, in this case Q, when? Well, it can, but we have to make the following assumptions. Either that Q is uniform. If Q is uniform, it gets out of the integral, and G is a known function. I integrated to obtain another new known function. This another known function is simply 1 over H. Okay, so this works well if I have a uniform heat flux. By the way, I can present things in a different way and still obtain an operator between delta T and Q. And if delta T was uniform, then we come back to delta T is equal to 1 over HQ. So the H model works well if I have uniform heat flux or uniform temperature. A moment. Have you ever seen a correlation in the literature for H anything else? It's always either the uniform heat flux heat transfer coefficient or the uniform wall temperature heat transfer coefficient. There is no other correlation. I have never seen that, which means that, okay, the correlations we have are not wrong, but we use them wrongly. We use them for anything, even if Q was not uniform, or even if the difference was not uniform. And by the way, none of these cases exist in reality. In reality, it's very difficult to have uniform heat flux or uniform temperature. So we are using the wrong model almost every time. There is another option, is to assume that the green function is a Dirac. In this case, the integral will boil down to the same result, delta T is equal to 1 over H times Q, which means that we have a local H, and this, we have seen before, completely contradicts problem physics and problem mathematics. And by the way, this is the real form of the weight or the green function. It is the highest at the point, I want to calculate delta T at the point X dash. So the highest weight will be Q at this X dash. But I still have a relatively correct weight for heat fluxes upstream of this point. And it may go to zero very rapidly downstream if the Pictet number was high. But it is not a Dirac. It is never a Dirac. We have obtained this for many special cases where we can do that analytically, circular cross-section duct or two parallel plates, and we have obtained G, and we know it analytically. It is not a Dirac. It is this form I have shown here on the right. Now I go to the FlexPro compact model, which I'm proposing to replace H. Suppose that I recognize the fact that Q may be function of X over, for example, on port A, it is QA is function of X, maybe developed over Taylor series or something like that. And I also recognize that the temperature at port A may not be uniform. It is a function of X, okay? Now, I will do that for all other ports, B, C, etc., whatever I have, any number of ports I may have. And then I will try to, if I substitute these developments in the original model they have proposed, where you have an integral green function Q that is equal to delta T, then this transforms down into a larger matrix. We have at the left a vector composed of all vectors of temperatures at each node. A vector for TA, which means TA node, TA1, etc. A vector for TB, a vector for TC. On the left, we have a large vector for all Qs, heat fluxes over each port, QA, QB, etc. And these are related by a matrix. Two vectors are related by a matrix. And how do I obtain this matrix? I just substitute the developments and perform the integration over the known function G. This will give me the matrix. We have many main advantages. First, we have one and the same model for any type of boundary conditions. It works well if I give you the temperature to obtain Q or give you Q to obtain temperature. We're using one and the same matrix. The heat transfer coefficient model is not a boundary condition independent model. In fact, its name says that. We say the uniform heat flux heat transfer coefficient or the uniform temperature heat transfer coefficient. That is, we recognize that the heat transfer coefficient is not the same depending on the type of applied boundary conditions. It's not a boundary condition independent model, which means it's a very bad model. But here we have a matrix that works well with any type of boundary conditions, uniform or non-uniform, given T or given Q or given anything. It deals with any inlet temperature profile and with any geometry. There is another advantage, which is, I have called it the precision knob. In fact, actually, we have only two extremes. Either to solve heat transfer problems, either we use finite element, finite volume, whatever, which is completely complicated thing. We make meshing and a large number of unknowns and numerical solution, etc., which is very precise but very slow. Or we have the other options. We have nothing in between, in which we use the heat transfer coefficient or anything and transform our domain into a small set of resistances, which is very fast. You can do it on hand in a couple of minutes, but simply really not precise at all. With the model I'm proposing, I have a knob and I can change as I wish the level of precision on the expense of speed. If I represent my temperature and my heat flux profiles over each thermal port using a few number of terms in the series, then this is a low precision. Okay, but I will have also a very small matrix because the number of unknowns is small and it will be relatively fast. And I can virtually go to only one coefficient on each port, that is uniform temperature or uniform heat flux or whatever. So I come back to the H, in fact, level of precision, which is a very bad precision. Or I can use a larger number of terms in the Taylor series expansion of temperature or of heat flux or of both, and in which case I have a very large matrix. I can go up to the analytic solution if I want. So, which will be very precise, but very small, very slow. Okay. There's another big advantage is the fact that I can decompose a complicated structure into smaller structures that are simple and then join them together. Suppose I have a small structure like a Lego element, just a box. I can obtain this compact model, but using our approach, which is temperature and heat fluxes can be variable on each face. And then I get another object and then I join them together. Joining them together is very simple using our approach because we don't assume that at the interface we have uniform heat flux or uniform temperature or whatever. They are variable, which is the real case. And the only thing I have to do is to say that the variable heat, for example, the variable temperature on one side should be equal to the variable temperature on the other side, as well as the variable heat flux from one side goes to exactly the variable heat flux on the other side. If I do this, I can join easily to the two matrices, and I'm making no approximation. If I had used the H, then there will be a strong error because I have to assume either temperature is uniform or Q is uniform, which is not the case. I can also add another element and another element, etc., to build a complicated structure out of simple structures by joining the compact model of each structure made alone. There is another advantage of the over the heat-transfer coefficient, which is that of symmetry. In fact, conduction is a symmetric problem. And we know that because in conduction we only have second-order derivatives and not first-order ones, which appear in convection problem. The term v dot grad t, this is a first-order derivative, and it only appears in convection. But in conduction, it doesn't exist. So the conduction problem is symmetric. What do I mean by symmetric? Suppose I have a resistance, temperature T1 on the left, T2 on the right. This will give me a certain heat flux between the two. I will call it Q of case 1. Now suppose I interchange temperatures. I put case 2, temperature T2 will be on the left and T1 will be on the right. This will give me a heat flux that is exactly the same, maybe difference in direction, but exactly the same as a value, or as an absolute value. This is the symmetry I am speaking of. I'm thinking about. But in convection, this is not the case. Suppose I have a duct where fluid is flowing, and I'm heating on the left side using a candle, for example, and I'm cooling on the right side using ice boxes or something like that. Then inside the domain, the temperature of the fluid will be high in all the domain, except just near the exit where it will be cooler due to the presence of ice boxes. Now, if I interchange them, and I put the candle on the right and the ice boxes on the left, then the temperature inside the whole domain will be low, almost that of the ice boxes, and will be only high just near the exit. So it's not symmetric. It's not like conduction, which is symmetric. Okay. By the way, the matrix I have obtained for using the green function that I have developed is a non-symmetric matrix. It exactly reflects this non-symmetry relation that H fails to capture. H is a resistance that is a symmetric element. Convection is not a symmetric issue. So modeling using H is wrong. or not sufficiently accurate. I mean, it's another way of saying. Another advantage is if I have a multiple heat source. Suppose I have many different heat sources that are not triggered at the same time, or do not have the same heat flux in general. Can I define H in this case? Between what and what? Between which temperature and which heat flux? I have many temperatures and many heat fluxes. The only way I can model this is by a matrix relating heat fluxes and temperature, which I am proposing. Now, there is another fundamental concept that I have to introduce about the fully developed and developing zones in heat transfer, convection, forced convection heat transfer. Suppose I have a uniform heat flux heating a duct, and I have here the evolution of the boundary layer, which will increase until it reaches the axis of symmetry, in which case the boundary layer will no longer evaluate. And if I want to calculate, for example, the heat transfer coefficient, I will find that it is variable at the entrance, and then it becomes constant after a certain distance. We call this normally the developing or developed, developing if the boundary layer is still growing, and developed if the boundary layer no longer grows. Okay, this concept, I believe, may work if I have a uniform heat flux. But if I have a non-uniform boundary condition with a non-uniform heat flux or non-uniform temperature or whatever, how can I say what is the developed and what is the non-developing and developed regions? Because both temperatures and heat fluxes will change along the whole tube. If the outside heat flux is imposed heat flux is variable, then nothing will remain constant. But I still have something that happens at the inlet and that no longer happens away from the inlet. So I can still define a developing zone and a fully developed zone, but I have to change my definition. Suppose I have a non-uniform heat flux, as we can see, and then at the inlet I may have different inlet profiles, either flat or parabolic or fourth degree or whatever. Then what happens is the following. At the entrance, the temperature in the fluid at the entrance will be function of the inlet temperature profile for a short distance. After this distance, it may still change due to the fact that I have a variable heat flux, but it will no longer depend on the inlet of the assumed inlet temperature profile. This is the new definition of developing and fully developed, which reduces, I mean, if I have a uniform heat flux, it will give me the same as we had before, but now it has been generalized to non-uniform boundary conditions. I have solved this numerically, analytically, using some numerical example for flat plates analytical solution. We have a 1 meter duct and a variable heat flux imposed and a variable also inlet temperature imposed. Now, I have supposed that the heat flux increases linearly, very simple case, and then I have 3 different temperature profiles at inlet, and I'm going to examine the temperature profile inside the fluid at section AA near the inlet, at section BB a little bit far, and at section CC a little bit further also. And let us see what happens to temperature profiles over each section. First, over the section AA, I found temperature profiles are different. The blue one for the uniform inlet, the parabolic is the brownish red one, and the green one is the 4th degree inlet. So we can see that temperature profiles inside the fluid, very near to the inlet, it was section AA, at Z equals 0.1 meter from the inlet. They are different. But if I go to section BB, which is at the middle of the tube, all the three profiles are the same, whether I had an inlet uniform or an inlet parabolic or an inlet fourth degree, then the temperature distribution is exactly the same at the section BB. So we say that here we have a fully developed flow. It's not that this temperature profile will remain constant further downstream. It will change further downstream, but it will not change as a function of inlet. It will no longer change. For example, let's see the CC section. You have another profile, okay, because you have another heat flux, okay, but we have the same profiles from the same three inlets. So this shows that there is something behind this new generalization. It's when the inlet temperature distribution no longer influences what happens in the duct. This is called the fully developed flow. And the entrance zone is a zone, or the developing zone is a zone where inlet have an influence on the temperature profile inside the tube. Another problem that has been solved to show the strength of this new approach is that of a conjugate heat transfer problem. I made a model in the form of a matrix for the fluid. I made another model in the form of a matrix for the solid, and then I have joined the two together. I have assumed nothing about the interface temperature distribution or the interface heat flux distribution, but I have added a uniform heat flux at the outside of the solids, and in order to see what will happen. Notice that this is a very basic problem in heat transfer of a uniform heat flux for a circular sectional duct. And I have drawn both the interface temperature and the interface heat flux as a function of x, both using my approach, it's called the CTM, and a finite element or a numerical solution approach. Okay, we see that neither the heat flux is uniform nor the temperature is uniform, but the CTM was capable of predicting the exact variation, almost the exact variation, compared to the numerical solution. I have done this also for a rectangular cross-section, but rectangular cross-section, we can no longer obtain the green function analytically. But we can do something that is very simple. I mean, analytically, we have transformed the partial differential equation, which is a convection diffusion problem, into a very simple Poisson's equation. Laplacian f is an unknown function, is equal to s, which is a known function. This Poisson's equation can be readily solved numerically. I mean, it's a basic equation. Anyone can do that numerically to obtain the same results, that is, the model prediction and numerical solution prediction. I have made many curves showing that they are the same. Finally, the transient problem. We all know that if I drop a thermometer in a hot bath, it will take time before it reaches its temperature, its final temperature. And we model this normally by putting a thermal resistance and a thermal capacitance, but this is based on the assumption that the temperature of the mercury is uniform. In fact, you have a bulk amount of mercury in the bulb and a very small quantity outside. So let's say that the temperature of the mercury is almost the same everywhere, but variable with time. Why don't we do that with convection? Suppose I have a fluid flowing over a plate or inside the duct or whatever, and I'm heating in a transient way. Suppose I start with Q equals to 0 and then increase the heating with time. The thermal boundary layer will develop with time. At the beginning, it's rather thin because I still haven't put enough time of heating, and then it will grow gradually. How can I model this? I can model this using thermal resistances. It's completely stupid, and because this is a capacitance effect. I have to model this using capacitances and resistances. They can be different set of RCs because we don't have the same temperature in the fluid. It's not like the thermometer where we have assumed uniform temperature. But I cannot assume uniform temperature, of course, in the fluid. It is being heated. So I have a different or variable RC that should be used to make the model that are space dependent. Do we have them? I would say not yet, but this is a work in progress, and I have a paper that is being reviewed now where I have done this correctly, in fact, semi-analytic way. But I am now doing that's something that I've already published. It's just a demonstrative example. I had two parallel plates, between them a fluid, and then I have put a step function heating that is 0, and then at a certain time it becomes another value, which is a constant value. I have obtained temperatures everywhere, and then I have concentrated on temperatures at the first section, x equals something, whatever. And I have drawn the temperature distribution of both the bulk temperature and the wall temperature as a function of time at this cross section. And I have deduced, if I want to apply the heat transfer coefficient concept, delta T over Q or something like that, that H starts with a rather high value and then quickly diminishes to a value that doesn't change with time. And this is what almost everyone, many papers I have found in literature were doing that. They are modeling this problem by a time-dependent heat transfer coefficient, which in my opinion is completely wrong. In order to show that, I have made curve fitting, just curve fitting, to using RCs, and I found that I must have two RCs in series in order to almost completely well fit the results of temperature, wall temperature, and bulk temperature at this cross section x equals to 1 with the very simple network. Of course, I would have used another values of RCs at other cross sections. This is a tedious work. I will not do this curve fitting every time. Now, in my new paper that is now being reviewed, I obtain these RCs analytically for any cross section. In conclusion, FlexPro, this flexible profile approach, is a paradigm shift in modeling. It can be used for conduction, forced convection, as well as conjugate heat transfer. In this case, the relation between delta T and Q is no longer a scalar, which is H or 1 over H. It is a matrix now. This has many advantages. It can be used for uniform or non-uniform boundary conditions, and any type of boundary conditions, by the way. And it can be used for any inlet profile, flat or non-flat. It has an adjustable level of accuracy, and it correctly handles convection dissymmetry, and it can model a complex system by joining complex models of elementary parts of it. Now, this is in a work in progress now. More will be obtained in the very near future. If you want to know more, then these are some publications. They can be all downloaded from the website I'm giving you down here. And I would welcome any cooperation to obtain the compact model, the FlexPro model, for different cases. I have done this already for a tube with circular cross-section as well as 2 flat plates. But we still have a lot of things to do in order to replace the well-known heat transfer coefficient in all the cases that you can find in standard textbooks. We still haven't done this, but we are progressing. So until we do that, you can still enjoy using H that you can obtain from textbooks, but not for long, because we will replace them very soon. So stay tuned. Thank you.